Okay, my name is Skip Robinson, and I'm going to demonstrate how my wind turbine works. It's not on my YouTube channel. You can see the actual working of it out in the wind, as well as the water turbine. So I'm not going to really demonstrate how it works in the wind. You can see that on the other video. But I want to demonstrate it because you don't really see a lot of the working mechanisms, how it really works. And there's a lot more physics involved than you would think from just looking at it spin. Anyways, first of all, it's an omnidirectional system. If you're the wind, comes in, hits this panel, pushes this panel, hits this panel, pushes this panel, pushes this panel. If I'm the wind, same thing. So no matter what direction the wind comes from, it picks up and will spin. In this case, the way this one is designed, in a clockwise manner. If you put the panel on the other side of the structural arm, it will spin in the other direction. So it's both omnidirectional plus it's bidirectional. You can get, if you want to, if you have a certain generator or a certain electrical system that you need, it's a motor that needs to be run one way, then you could, of course, just switch panel from one side to the other. What's nice about this particular turbine, what fascinated me about it, was that the wind, when the wind pushed on this panel, it was a lot of area and a lot of power at low wind speed. And this thing actually this little one will actually turn when you're just walking with it, carrying it around. That's how little wind it takes to, and the same thing, 5 miles per hour pushes this thing pretty quickly outside. So, it does capture a lot of kinetic energy from the wind because of the large sail. I call it the sail side, or the windward side of it. And conversely, because of the flipping panel, the reduced drag as it comes back against the wind, and that's what you're looking for. You're looking for the greatest amount of power with the least amount of drag on the system. So that's what kind of spiked my interest when I initially started playing around with it and decided to build this little model. It's a working model, as you can see in the other. I just thought it would be easier to take apart and disassemble and re-weld and re-solder. It's made with basically balsa wood, brass tubing, and I've got little bearings not only in the center shaft, but I've actually got little bearings on each one of these panels. There's 2 bearings, one at the top and one at the bottom, or middle of the panel. So here's kind of how it works. As the sail panel gets pushed, of course, it's being pushed up against the structural arm. It's going to stay in that position. As this one comes around, I finally realized right away that this panel, the faster it spun, the more the panel wanted to stay out because of centrifugal forces. So I had to come up with an idea that would make that panel come into the structural arm. I thought the wind, when I was first playing around, I thought that wind would push it and keep it straight. Well, the spin is so hard that it keeps it out. So what happened was I kind of killed 2 birds with 1 stone. At this point, this panel is being pushed, this one's coming back against the wind, and this one at this point, if you're the wind coming towards me, the wind gets behind this panel, flips it out, and what I've done is I've transferred through a cabling system. I've transferred the torque of this panel, and the power of this panel, which would be wasted if it just flung open. That would be wasted energy, and not only that, it would throw the whole system off. So I figured out a way to transfer this system so that it pulls this panel in. And this force seems to be strong enough to pull the panel in, which is kind of just by pure luck and coincidence. Anyway, so that's kind of how it works. As each panel, this one becomes a pusher, then this one flips open and pulls that one in. This one flips open when it gets to here, pulls that one in. And Now this could be done. I've created a little cabling system that took me longer to figure out than building both prototypes, designing it, getting it patented. All that took me longer than figuring out this cabling system. My initial thoughts was to do a hydraulic system. I still think the hydraulic system, a very low pressure hydraulic system, would be very, very good. Right, what I want to do is incorporate what are called rotary actuators into each of the hinges. So as this panel gets flipped open, it pushes the hydraulic fluid and closes this one. This one's already closed. So it's just a closed loop system with all three panels hooked up, and as each panel flips, it's going to go to the weakest point, which is this. This one's being pushed by the wind. It's not gonna have an effect on that. And so hydraulically, it would work just the same way, except that you'd have a much tighter system. You know, I could control my stops perfectly so that it doesn't slap. Right now, in the video, you'll see it slaps up against the bar. Well, I don't have any cushions or anything on it, so it just makes a little noise. But if I had a hydraulic system, I could get it to stop before it hit the bar, and I can get it to stop any point on the flip, maybe 90. Right now I have it set on approximately 90 degrees, depending on how long my strings are. Pain in the neck to tie those, by the way. And so therefore, I could set the both stops exactly where I wanted to do with a hydraulic system. And so that's kind of how the system works. Like I said, the centrifugal force, once it gets up to real high speeds, what happens, it just spins like this. You know, you get up to 15 with this little one. Understand that, yeah, this is an interesting point too. You understand that the farther out you go, let's take you take the average person walking this far out. So the farther I extend this panel out, the slower the wind turbine is going to turn, because 5 miles per hour at this speed is much slower than 5 miles per hour at this speed. So there's a torque or power to speed ratio, or actually RPM ratio, that people can play around with and develop what they think is best. You know, a gearing system can transfer a slow speed to a fast speed, so there's no problem developing a difference. And I know the system works to put a load on it, so I mean, you can just feel the tube, and when you put a load on it, so it works quite well, and it works quite well under load. The water turbine we have placed under tremendous load, and we were able to get on with panels that are in the water now. Water is 800 and sometimes more dense than air, but in the water, using a 2.5 foot panel by 1.5 panel, but 2.5 foot tall panel by 1.5 foot tall wide panel, we were able to get over 300 pounds worth of force out of a small little water turbine prototype, using a load cell and putting up on the front of a boat, pushing it at various speeds to try to determine, you know, efficiency, basically. So that is in the hands of Hydro Alternative Energy now. They have the water patent, and how they're progressing is, I've heard that the engineers are working around the clock on it, was the last thing I heard. So we'll see how they come along. They've got a couple projects set up around the world, one in South Africa, I think. So with all that said and done, that's basically what I wanted to show you today, how many physical components are actually taking place, and why I thought this was a neat design. And so I am preparing to build a larger one, and I think I even have a better idea. So I will be working on that in the next few months, and hopefully in 90 days or so I'll have a full size. I'm probably going to make my panels 4x8, just to give you an idea of how big it's going to be. And I'm having engineering companies come up with hydraulic actuators for the 6 hydraulic actuators to run the system. And what'll be interesting is the the hydraulic lines will just be inside the tubing, so they'll be out of harm's way. You use airfoil on all the tubes, and you're going to even eliminate a greater degree of drag. So that's pretty much it. Thank you.